In this lecture, I'm going to start the design of threaded fasteners. So I'll give you the introduction about threaded fasteners and the standardization of threaded fasteners today. And in the next lecture, we will see how to design the screw joints. So we'll start with the screw joints. So the screw joint is mainly has two components. One is the bolt and the another one is nut. So these bolts and nuts are used to connect the two bodies in a temporary manner. So screw joint is not a permanent joint. Whenever we need to dismantle the joint, we can loosen the nut and we can remove the jointed components. Okay. So screw joint comes under temporary joint, and the advantage of screw joint is whenever we need to remove the components, we can dismantle it. Okay. So it's a readily available joint. You can easily connect and you can easily disconnect without any damage for the machine. The advantages of screw joint. So the first advantage is, so the screw joint is very convenient for assembly and dismantle. Okay, so as I told you earlier, it's easily connected and it's easily disconnected without any damage to the machine. Then the second point is a wide range of screw joints may be adapted to, so different range of screw joints are available. For we have a set of set screws. We have different cap screws. We have different diameters of bolts and nuts. So this different types of bolts and nuts can be used for suitably selected for your given applications. So that is the second advantage. And the third advantage is screw joints are relatively cheap to produce. So comparing with the welded joints and riveted joints, the screw joints are really cheap. Okay, so the amount of producing a single screw joint is low comparing with the other kind of joints. The disadvantage of screw joint is stress concentration. Since we have a varying cross section throughout the length of the screw, we will have stress concentration at all the regions. Okay, so because of the stress concentration, the material will fail or the screw joint will fail before it reaches the ultimate stress of the material. So that is the only disadvantage of screw joints. The terms used in screw joints. So the maximum diameter, the outer diameter is called as major diameter. The inner diameter of the screw, that is the minimum diameter, is called as minor diameter, or sometimes it is called as core diameter. Okay, so it may be called as DC, the diameter of the core, and the nominal diameter is called as pitch diameter. Okay, so the average between the major diameter and minor diameter is called as pitch diameter, and it is denoted by small d. Okay, so in the thread profile, the outermost point is called as crest. So this point is called as crest, and the bottommost or innermost point is called as root. Okay, so just like the tree root, the bottommost point is called as root. So the difference between the vertical distance between crest and root is called as the depth of thread. Okay, so the outermost point is crest and the innermost point is root, and the vertical difference between crest and root is called as depth of thread. Okay. Then the horizontal distance between consecutive crest points or consecutive root points is called as pitch. Okay, so the consecutive distance between, I mean the horizontal distance between two consecutive threads is called as pitch. Then the inclined profile of the thread region, so this region is called as flank of a thread. The inclined profile of the thread region is called as flank. Okay. Then the angle between two adjacent flanks is called as angle of thread. Okay, so we have a V-like profile for flank, and the angle between the two flanks is called as angle of thread. So the angle of thread will be around 40 to 60 or 65 based on the standard. Then at the end we have half of the pitch, that is the distance between crest and adjacent root is half of the pitch, 0.5 times the pitch diameter. Okay, so the terms are very important. The outermost point is crest, innermost point is root, and the vertical distance between crest and root is depth of cut, and the horizontal distance between two adjacent threads is called as pitch. The inclined profile is called as flank, and the angle between two inclined profiles is called as angle of thread. The maximum diameter is called as major diameter. The inner diameter, that is the diameter of the root, is called as minor diameter or core diameter, and it is denoted by dc. So the nominal diameter, that is the average diameter, is called as pitch diameter, and it is denoted by small d. So there are different standards of screwed threads are there. So the first one is British Standard Whitworth thread, BSW thread. Okay. So in British Standard Whitworth thread, we have a V profile, and the angle of thread, that is the angle between two flanks, is 55 degree. Okay. So this is the main point about BSW thread, and this thread is used for some special purpose applications like fluid carrying applications. In some of the applications, we are using threaded joints to connect two GI pipes. So where the GI pipes are used to carry some fluids. Okay. So in that case, we can use this BSW thread since its angle of thread is very minimum. Okay. Then the second profile is British Association thread, BA thread. So here also we have a V profile of thread, and the angle of between flange or the angle of thread is 47.5 degree. Okay. So this kind of BA threads are used in some instruments and other precision work. So this BA thread is used in most of the measuring instruments and other precision works. Okay. So this thread is not used in any fluid carrying application or any not used in any load carrying application. It is mainly used in measuring instruments. Then the third one is American National Standard thread. So it's very common thread. So this kind of threads have a V profile with a 60 degree angle of thread. So 60 degree is common, and this kind of threads are used in the general purpose applications like bolts and nuts and all the kind of screws. So where it is used for carrying some loads. Okay. So in our day to day life, what the thread we are using is American National Standard thread. So actually we have a different metric thread as per Indian standard, but the metric thread is a slight modification of American National Standard thread alone. Okay. The next one is square thread. So here the thread profile will be like a U structure. It's not a V structure. Okay. So here the angle is same, and this kind of square threads are used in high load applications like your lead screws. So in lead screws, in lathe, the lead screw is used to uh, feed the depth of cut, and in some of the screw jacks, this kind of screw threads are used for high load carrying application. So this square thread is mainly used in load carrying application. Then the second one is ACME thread. So this is also like it's a slight modification of screw thread alone. Here the angle of thread is 29 degrees. So here also it is used for high load carrying application like the machine wise, then high load carrying valves, and in some of the screw jacks and other kind of load carrying applications, this ACME thread is used. The finally metric thread. So metric thread is based on Indian standard, and like American standard, in metric thread the angle of thread is 60 degree. Okay. So this thread profile is generally followed in India, followed by Indian manufacturers for manufacturing screws, bolts and nuts. So it's a general purpose thread, and it is used for low load carrying applications. So we have different types of screw fastening. The first one is through bolt. So in the through bolt, the consider two plates. The screw is inserted, and in the opposite side, the nut will be used to tight the screw. Okay, so the screw covers the overall length of the plate. That is why it is called as through bolt. And the second one is tab bolt. In the case of tab bolt, there is no nut is used, and the threads are formed in the plate itself, and the bolt is used to tight the two plates together by using the threads in the plates. So there is no nut is used. And the third one is stud. So in the case of stud, there is no cap for the screw. So two nuts are used. So here also the threads are formed in the plates, and the stud is used to join the two plates by connecting the by threading the two plates together using the stud. And in some cases, one nut may be used on the top part to give some additional tightening torque. Okay, so the initial load for tightening is called as tightening initial torque, and in some cases a single nut is used. Then cap screw. So in cap screw, there is no nut is used, and different kind of caps are used for initial tightening. Okay, so the first one is hexagonal head. So we can use the screw, I mean spanners for tightening and loosening of the hexagonal head. And the next one is philister head. So you can use a screwdriver for this. Similarly, for round head also you can use a screwdriver. Then we have flat held. So this is used in most of the applications. Then we have hexagonal socket. So here you can use the align keys. Then the most rare one, it's fluttered socket. Then the next one is set screws. So in set screws, we don't have a cap. Actually, in cap screws, we have some cap structure for initial tightening and loosening. But in set screws, we don't have a cap. And in most of the set screws, the align keys are used for tightening applications. Okay. The design of bolts subjected to external loads. So in general, the bolts are subjected to three kind of load. The first one is tensile load, the second one is shear load, and the third one is combination of tensile load and shear load. So first consider the tensile load. Assume that a load is acting like this. So when the load is acting like this, the stress will be induced on the thread, and the concentration of thread will be maximum at the root region or the inner diameter. That is, the DC is subjected to high amount of stress. So we know that the stress is equal to sigma is equal to load by area, F divided by A. Further, F is equal to sigma into A. So F is equal to, here because of the tensile load, the tensile stress will be acting on the stress. That is why I have considered sigma T, and the area is pi by 4 d square. So here, as I told earlier, the concentration of stress will be maximum at the core region, that is the root point. So that is why I have considered pi by 4 d c square. And n is the number of bolt. In the case of single bolt, then we can neglect the number of bolts. In some of the structures, the load is evenly distributed, evenly carried by 3 to 4 bolts. In that case, you have to consider the number of bolts. So in the equation, F is the externally applied load, sigma T is the allowable tensile stress of the bolt material, and N is the number of bolt, and DC is the root diameter that we have to calculate. So this is the first type of load. And the second one is shear load. So whenever a twisting moment is applied on the bolt, then it feels a shear load on it. And we know that the equation for torque is T is equal to, tau is equal to T into R divided by A. So T into R will give you torque into radius and into A. So you can write T divided by R into A. So T is equal to tau into R into A. Further, T is equal to tau into R. In the place of R, I have replaced D divided by 2. That is, bolt circle diameter divided by 2 will give you the radius. And the area is pi by 4 D square. So here, while the twisting moment is applied, this point is subjected to high amount of stress. Okay, so throughout the flank, it feels uniform amount of stress. That is why we have considered the nominal point or nominal diameter, that is D. So here the area is pi by 4 D square and N is the number of bolt. So in the equation, T is torque, capital D is bolt circle diameter, and tau is allowable shear stress of the material, N is number of bolt, and D is the nominal diameter that we have to calculate. So in tensile load, we have to consider the minimum diameter, that is DC, and in the case of shear load, we have to consider the nominal diameter D. So the third one is the bolt is subjected to both tensile and shear load. So in this case, first we have to consider the tensile load alone and we have to calculate sigma T. Then we have to consider the shear load and we have to calculate the tau value. Then after calculating sigma T and tau, we have to use the combined stress equations. So if the sigma T is given in the problem, then you can use the maximum principal stress equation. If tau value is given in the problem, then you can use the maximum shear stress equation and you can substitute the values and you can calculate the diameter of the bolt. So after calculating the diameter of the bolt, we have to standardize the diameter. Okay. So the standard diameter of bolt is available in the data book page number 5.42. So I have given you the scanned copy of that. So here the major diameter is outer diameter, pitch diameter is actually the nominal diameter D, and the minor diameter is DC. For example, in my problem I am getting a minor diameter of 2 mm. Okay, so this is the minor diameter or DC. So here it is 1.9 and the next standard diameter is 2.3. But in my problem I have got a diameter of 2 mm. Then I have to go for the next standard diameter and I have to select this 2.387 as a standard diameter. And for 2.387, the size of the bolt is M3. So my final solution is, the answer is M3. So this is the answer. Okay, so this is how you have to standardize the bolt diameter. So I'll finish this lecture with a simple problem. So it's actually a 2-mark problem. Two shafts are connected by means of a flange coupling to transmit torque of 25 Newton meters. So the torque is given, which means the bolt is subjected to shear stress. The flanges of the coupling are fastened by 4 bolts, N is equal to 4, of the same material at a radius of 30 mm. So the bolt circle radius is given as 30 mm. Find the size of the bolts if the allowable shear stress of the bolt material is 30 megapascal. So tau is equal to 30 megapascal. So here the bolt is subjected to shear load. So you can consider the second equation, that is T is equal to pi by 2 tau pi by 4 D square into N. So substitute the values. N is 4, D is diameter we have to calculate, tau is given as 30, and in the problem the radius is given 30 mm. So I have multiplied 2 to find out the diameter. Then the torque value is given in the problem, I have substituted it. So if you solve this equation, finally you will get a nominal diameter D, that is equal to 2.97 mm. Okay. So now the important point is we have to standardize the bolt diameter. So take page number 5.42. So the calculated diameter is 2.97. So and it is the nominal diameter. So here you can see the pitch diameter. Okay. So the pitch diameter is same as the nominal diameter and it is equal to small d. So after 2.675 I have 3.545. But the calculated diameter is 2.97. So I can select the next standard diameter, that is 3.56545, and for 3.545 The size of the bolt is M4. Okay, so the solution of this problem is we have to use M4 bolt. So M4 is the answer. Okay, so this is how you have to uh, calculate the diameter of the bolt, and we have to standardize the bolt based on the standard given in data book page number 5.42. So in the next lecture we will see how to solve the design of bolts for eccentrically loaded joints.